We're going to move on in number theory and start looking at prime and composite numbers, the number of divisors, the fundamental theorem of arithmetic, and factorization. So if I look at these blocks, the blocks represent the number 18, which could also be grouped as 2 rows of 9 or 3 rows of 6. So 18 has some positive divisors of 1, 2, 3, 6, 9, and 18. So I'm getting those numbers from what's on the side of the blocks. If I take those divisors and I list them across the top, we can identify numbers less than or equal to 37 that have a positive number of divisors. These numbers have exactly 2 positive divisors. So that's what I'm putting in this table. So numbers that have exactly 2. There's some numbers that have exactly 3. Those special groups would be numbers that are divisible by 1 and themselves, which is the definition of a prime number. So this column is all prime numbers. Notice that the number 1 is not in the prime number column. That's because the number 1 has only one factor. To be prime, you need exactly 2 positive factors. Everyone else has at least one factor other than 1 in themselves, so they are composite. So the number 1 is actually outside of this. It's neither prime nor composite. So a prime number is any number with exactly 2 distinct positive divisors, and a composite number has 2 distinct and 1 other, so a total of 3. So if I want to show that these numbers are composite, I just need to show that it's divisible by different numbers and it is composite. Since it's divisible by 2, that means it's divisible by 1, 15, 64, which would be our prime definition. But once I add that 2 in, I can stop. I've proved it's composite. I don't need to keep going with that. Same thing with 2781. Well, I can prove it's divisible by 3. So right there, I know it's composite because it has an additional factor other than 1 in itself. For 1001, if I look at that, it's going to be divisible by 11. So it's going to be a composite. And then if I look at this one first, I'm going to simplify it. So I'm looking at the product of its odd numbers. And then I'm adding 1 to it. All even numbers are divisible by 2. And all even numbers except for the number 2 are composite. So composite numbers can be expressed as either a product of 2 or more whole numbers greater than 1. And when we do that, we call that factorization. And if the factorization only has 2 values, the number and 1, the number itself times 1, that's called a prime factorization. So each composite number can be written as the product of prime numbers, except the order of the prime factors need to occur correctly for the product. To find the prime factorization, this is that tree method you probably learned in school where you're taking those numbers like 6 and breaking 6 into 2 times 3, which would be 2 prime numbers. And you're going to follow that process until you have all primes. So I know 84 is 4 times 21. Then I'm going to break 4 down into the product of prime numbers, which is 2 times 2, which we would show as 2 squared, and then 3 times 7. And so that would be my prime factorization. The same thing happens with 495. It's divisible by 5 and 99. I can then break 99 into 11 and 9 into 3 and 3. So the values in red are going to be the values that are part of the prime factorization. And these two trees, they produce a similar prime factorization, except for the order in which the primes appear and the product is going to be different. That's okay because multiplication is commutative. So the order that we write them in does not matter. Once we find the prime numbers, we just have to keep breaking them down until they're done, and then that's as far as you can take it. So if I wanted to go 2 into 260, that would give me 130. 130 is divisible by 2 as well. And I can keep going, and 65 I know is divisible by 5 because it ends in 5. And then once I hit 13, that is going to be prime. So I could see that as my prime factorization would be 2 squared times 5 times 13 times 1. How many positive divisors does a number have? Well, we're not asking how many prime divisors the number has, just any divisors. So in that case, I'm just listing out all the factors of 24. I don't have to do prime factorization on them because anybody is eligible. And this is the kind of the explanation for it. Another way to think of the number of positive divisors is to consider if I did the prime factorization, that would be 2 to the third times 3. 2 to the third, which is 8, has 4 divisors, and 3 has 2. So that would give me 6 total divisors, which is what we found earlier. And then I would have to continue out from there and consider the multiplication. Since I am looking at 21, the larger factors of that would also come into play. So if they're just asking you for the number of divisors, you're not going to consider and do prime factorization, although prime factorization can help, but you are looking at what are all the factors of that number. It's going to be a process in the lab. It's almost like a guess and check situation. If P and Q are different primes and M and N are going to be a whole number, then these have N plus 1 times M plus 1 positive divisors. What on earth does that mean? Well, let's look at this. The prime factorization of this number is going to be 2 to the 6th times 5 to the 6th. Okay, so 2 to the 6th has 6 plus 1 because it's coming from the exponent divisors. And 5 to the 6th has 6 plus 1 divisors. They each have 7 divisors. So I would take those 7s and multiply them together to get 49. So when we are looking at exponents and it divides nicely into a number with an exponent that way, then we can really nicely have the opportunity to multiply those together by adding 1. So now if I want to find the number of positive divisors of 210 to the 10th, I want to break that out into prime factorization. So I get 2 times 3 times 5 times 7 by factoring the number of 210. Then I'm going to do those plus 1 divisors with my fractions, and I'm going to multiply them together. So I would get 11 times 11 times 11 times 11, which would be 14,641. Now, if I'm just looking to see if a number is prime, I just have to check the divisibility rules. To prove something is prime is more difficult than to prove something composite. For example, 97 is prime, but I'm going to have to try dividing by those prime numbers, 2, 3, 5, 7, 9, 11, 13, 17, 19. So you have to go all the way up to the prime factors until you reach 97. The goal is to check all of those prime numbers leading up to that number. If none of those prime numbers divide into 97, then it's going to be prime itself. So it's definitely much more difficult to prove something as prime than to prove something as composite. And these are just some additional divisibility rules. So let's look at some examples. Is 397 composite or prime? So to prove that, I'm going to go ahead and start with my prime numbers and looking at divisibility. The possible primes would be such that when any prime number is squared would have to be less than or equal to 397. So that means once I hit 19 squared, anything above that is going to be greater than 397. So I stop there. I only have to check up to 19 because of this theorem on this slide. So I check all of those, and because it's not divisible by any of those, that number is prime. So that's a shortcut. So instead of having to check every prime number up to 397, I can say some prime number squared has to be less than or equal, and I can go from that direction. Is 91 composite or prime? So my possible primes would be 2, 3, and 5, and 7, because once I get past 7 squared, which is 49, it's bigger than 91. Because it's divisible by 7, it is composite and therefore not prime. One way to find all the primes less than a given number is to use the sieve of the Greek word. If all the natural numbers greater than 1 are considered or placed in the sieve, the numbers that are not prime are crossed out or drop through the hole. The remaining numbers are prime. So it's kind of a ruling out process. So this would be if I was steadily ruling out numbers that aren't prime. Now, this is a great screen to take a screenshot of because you're doing the prime numbers here, and I've already indicated who is prime versus who is composite all the way up to 100. So it benefits you to take a quick screenshot of this. And there is the completed prime number slot.